Okay, so the brightness is proportional to 1 over the distance squared. For example then, if we start off here at a distance of 1 unit, 1 square, whatever that 1 grid square, whatever that unit would be, if we go twice as far, okay, now we're 2 units away. So that's 1 over 2 squared, means it's 1/4 as bright here as it was if we were standing here. See, those light rays are spreading apart from each other, and it's how densely packed they are that is what we sense as the brightness. If we go to 3 times farther away, 1, 2, 3 units away, the brightness is now 1 over 3 squared as much. It's 1/9 as bright as before. You see how quickly the brightness gets very, very dim. If we went 10 times farther away, way out here, 1 over 10 squared, it would be only 1/100th. That's 1% as bright as if we were standing up here. All right, so things get fainter the farther away they are, which you probably had an instinctive feel for, but now you know why. We can use this then. We can take that luminosity and the flux that we've been dealing with, and we can work this out to where we can define a new kind of magnitude that depends only on the luminosity and not on the flux. That is not, and that therefore doesn't depend on the distance. This will be called an absolute magnitude, and we're going to use a capital M here to distinguish it from the apparent magnitudes, which we will always write with a lowercase m. Now, so in order to handle this then, we've given an arbitrary distance. We say, all right, if we were to move this star to where it was exactly 10 parsecs away from us, then how bright would the apparent magnitude be? Well, that's what the absolute magnitude is. It's the apparent magnitude when the star is at a distance of 10 parsecs. All right? If we put this into the magnitude equation, let me scroll back up here. All right? Remember, the flux here is in the apparent magnitude equation, but the flux, we go down here, depends on the distance, d, and the luminosity. So putting that in for the flux and saying that the distance is 10 parsecs, well, we've got 10 parsecs for star 1, 10 parsecs for star 2. Those cancel out, the 4 pi's cancel out, and we're left really with just the ratio of the luminosities. So the difference in 2 stars' absolute magnitude is depends only on the ratio of their luminosities. And since luminosity is a physical property intrinsic to the star, then so is the absolute magnitude. So flux corresponds to apparent magnitude, luminosity corresponds to absolute magnitude, and either one can be converted into the other. Flux to apparent magnitude, luminosity to absolute magnitude, and back and forth. But maybe you know the distance. And if you do, you can convert between apparent and absolute magnitudes, just like back here. We can convert between the the luminosity and the flux if we know the distance. Well, we can do the same thing with the distance, letting us convert between apparent magnitude and absolute magnitude. So if we write the distance in parsecs, and it has to be in that unit for this to work without any changes, then apparent magnitude plus 5, that depends on what units we're using for distance, but 5 here, minus 5 log of d, distance, gives us the absolute magnitude. There we go. To sum that up then, distance is the key. Flux and apparent magnitude can be converted into each other. Luminosity and absolute magnitude can be converted into each other. But the thing is that you can always get flux, or equivalently apparent magnitude. You've always got access to them. You can measure. You can take a photograph of them. You can take a telescope, hook up a camera, measure the flux, get an apparent magnitude from that. Then you've always got that. If nothing else, you can just look at it like Hipparchus did, and get a very approximate, but some kind of a rough apparent magnitude. If you can see it, you can measure that. The luminosity, or equivalently the absolute magnitude, you don't always know. You don't always have the ability to get. To get that, you will generally need to know the distance or something else about the physics. So I'm making these little triangles here. If we take flux and luminosity and distance, we see here that any two of these allows you to get the third. That's why I'm drawing the triangle. So you need two to get the third. Flux and luminosity gets you the distance. Luminosity and distance gets you the flux, and so on like that. Flux and distance gets you the luminosity. Or, if we can put it into magnitude terms, the distance lets you convert between apparent and absolute magnitudes, and again, any two of those three allow you to get the other third one. All right, that's that part there. And we're going to go on with a bit more about these.